Bismillahirrahmanirrahim. Assalamualaikum and a very good morning. Okay, we are still in the second week syllabus, which is the microwave waveguide part 2. So I have discussed part of the microwave waveguide components in the first part. So in these slides, I'll continue with the second part of the waveguide structure. Okay, so today we are about to discuss on planar transmission line. So if compared to the conventional waveguide that I have shown earlier, such as the coaxial line, rectangular and circular waveguide, so today we are about to look at the planar transmission line that's usually being used in integrated circuit or in planar structure. So planar, usually the structure can be printed directly on the substrate or the surface of the structure. So the advantages of this planar transmission line is low profile and lightweight, and it miniaturization of microcircuit, meaning that you can produce a smaller structure if compared to using a conventional structure, and easy fabrication since the material or the structure can be printed directly on the board, and it is tinned, and using thin film technology and photolithography, and it allows control characteristic impedance of transmission lines, since we can vary the size, the width, the dimension of the structure easily if compared to the conventional waveguide. However, the disadvantages of the planar transmission, its limited capability of handling high power, and it is lossy if compared to the conventional coaxial or rectangular or circular waveguide. And at higher frequencies above 20 GHz, the dielectric losses increase or is higher if compared to lower frequency, so that it limits the overall performance of the system. Right, so we are about to discuss on the microstrip line, strip line, and coplanar waveguide as an example of a planar transmission line. Okay, the first one is the microstrip line waveguide. So basically, the planar transmission line is part of the waveguide, but since it is printed on the substrate layer, so it is called a microstrip line or microstrip transmission line. Okay, the microstrip line is an electrical transmission line that can be fabricated using printed circuit board, and it is used to transmit microwave frequency signal. So the electromagnetic wave or the microwave frequency signal is traveling in between inhomogeneous medium. What does it mean? This is the microstrip line. It is being separated by a dielectric material and back with a ground plane. So you have a ground plane here, and here is your microstrip line, and this is the dielectric material. So the dielectric material could be the FR4 board, it's the standard PCB board, the Rogers, or even the textile material, so depending on the application. Okay, and the inhomogeneous, meaning that this material above here is air. Okay, it has different relative permittivity or dielectric constant if compared to the dielectric material. Okay, so the wave in microstrip line propagated through different property. Okay, for example, here the E field that is going out from the structure through the material, the air or the substrate. Okay, so the signal travels across two or more different medium, so it is called inhomogeneous medium. All right, so the relative or effective dielectric constant or permittivity epsilon r, basically representing the equivalent to homogeneous medium. Okay, so this one we consider the air and also the other materials involved in the signal propagation. Alright, so there, yeah, as mentioned, the microstrip line consists of conducting strip. Okay, this is the conducting strip separated by from a ground plane by a dielectric layer. Okay, these are examples of the microstrip line, in which you can see there's a line lies on the board. Okay, the board is basically the this is the dielectric material, probably the FR4 or the PCB board, and back with the ground plane. Okay, the ground plane usually having the same property as the strip line or the conductor. Okay, as in the rectangular and circular waveguide, so the dominant mode for the microstrip line is quasi TEM mode. Again, it is no TE10 or TE01 or TM10 mode. Okay, it is quasi TM mode. Okay, the figures show the 2D plot of field power density distribution of shielded microwave transmission line at 20 GHz, and the size of the structure or the microstrip line in terms of the width of the strip, the thickness of the insulating layer, PCB or ceramic. Okay, this is the dielectric materials, and the dielectric constant of the dielectric determine, okay, will affect the characteristic impedance of the microstrip line. So we are going to discuss in details in terms of the equation related to the Z0 in the next session. Okay, basically in the design process, you need to properly determine the width of the and the thickness of the microstrip line, so because it will control the how the field propagated and how what's the frequency for is it suitable for the targeted application, and how about the radiation and etc. Okay, the slide summarizes the equation related to determining or calculating the width of the microstrip line, which include the thickness, h, the relative permittivity, okay, the area, and etc. So each of these can be determined by the following equations, and the effective permittivity of the microstrip line due to different permittivity involved in the signal transmission, so can be simplified by using this equation. So basically that's the calculation has been made simpler by using a calculator. Okay, there's an online calculator in which you can use that calculator to calculate the dimension of the microstrip line, okay, prior to the design. So once you have all the dimensions, then you can use that values into your simulation tools or simulation software, and then you can simulate whether you can get the response or the frequency you are targeted on or not. Okay, the following equations 7 and 8 basically representing the characteristic impedance Z0 of the microstrip line and also the length of the microstrip line. Okay, so C here is the velocity of light in free space, so that's related to the wavelength of the targeted frequency band. Okay, additional information about microstrip transmission line. So the higher the impedance, the higher the dielectric constant or the permittivity, the thinner the microstrip line, keeping the thickness of the dielectric and impedance of the line constant. While the thinner the dielectric structure, okay, so you have the microstrip line, and then you have the dielectric. Okay, back with the ground plane. Right, so the thinner the dielectric, the thinner the line is. So the line meaning the edge of your microstrip line, keeping the dielectric constant and impedance of the line constant. While the higher the dielectric constant, the smaller the circuit is, and the wider the lines, the lower the impedance. Okay, we are going to look at the effect of those parameters in the later session. Okay, next is the strip line waveguide. Look at the difference between the microstrip line and the strip line waveguide. Okay, the strip line waveguide uses a flat strip of metal which is sandwiched between two parallel ground planes. The insulating materials of the substrate forms a dielectric. Okay, if compared to the microstrip line just now, you can see that in microstrip line you have the lines on top of the dielectric. Okay, back with the ground plane. This is the microstrip. While in strip line, you have the lines being sandwiched in between two dielectric substrate and back on top and at the bottom by a ground plane. Okay, so you have ground plane and you have another ground plane. Okay, your strip line is in the middle and then separated by dielectric. Okay, that's the difference between strip line and microstrip line. Okay, another type of the planar transmission line is the coplanar waveguide, or called CPW. Okay, in CPW, the structure is more or less the same as a microstrip line, but it includes three conductors separated by smaller gaps. Okay, you have three conductors, the first one, the center one, and the third one, that printed on the same side of the substrate. Okay, just like the microstrip line, hence it is called coplanar. Okay, the return conductors are separated from the central, so this is the central. The return conductors, meaning the first one and the third one, separated from the central track by a small gap, so G. Okay, the gap in between those conductors and also the central line. And then the electromagnetic wave carried by a coplanar waveguide exists partly in the dielectric substrate and partly in the air above it. Okay, so the E field traveling outward from the structure. Okay, in between two different dielectric constant or permittivity of different materials in air and also in dielectric, so just like the microstrip line. So the dielectric constant of the substrate will be different and greater than the air in which wave is traveling as in inhomogeneous medium. Okay, inhomogeneous medium has been discussed in the previous slides. And in terms of the mode, CPW or the coplanar waveguide will not support the true TEM wave at non-zero frequencies. But the major problem with the coplanar waveguide is that it having non-unique characteristic impedance. Okay, because of the infinite range of ratio between the center strip width and gap width. Okay, the center line width W with the gap width G. Okay, in practical, for the Z0 for microstrip line is unique. That's decided by the strip width, substrate height, and substrate permittivity. So we are going to look at this calculation in the design process. The advantages of the CPW or coplanar waveguide in comparison with microstrip: it is easier grounding or surface mounted, it's lower fabrication costs, reduced dispersion and radiation losses, and photolithographically defined structures with relatively low dependency on substrate thickness. Okay, because as mentioned earlier that the property or the Z0 of the microstrip line is decided by the strip width, substrate height, and permittivity. Okay, so substrate height meaning the thickness of the substrate. But if you are using the CPW, so you can have a structure that more efficient structure by low dependency on the substrate thickness. Okay, next is the horn waveguide. So I believe that you have seen this kind of waveguide in your third year PBL lab, so in which during the lab you are required to design a horn antenna with to achieve certain gain and also targeted frequencies, and you have played around with the width and the height of the horn to get the response or the performance as required. Okay, so this is another example of horn waveguide. It is custom made for 47 GHz and it achieved 20.3 dBi gain. And another one is the cavity resonator, and this has been done in the second year PBL lab, microwave lab, in which the cavity resonator you have two metal plates in which the separated by a cavity or empty space, and this technique is usually being used to measure the permittivity or the property of the samples or the materials. For example, in the second year lab, I think EMT lab, there's a hair fiber materials that being placed in between the cavity, okay, inside the empty space cavity, so that the property or the relative constant and the conductivity of the hair fiber can be determined by measuring the permittivity by supplying the current and also voltage across the cavity. Okay, so we are going to look at these examples later on. Okay, that's another examples of cavity resonators. Okay, the difference in the shape and the size of the structure depending on the samples you are about to measure and depending on the application it will be used on. Okay, that's another example of cavity resonators for different applications. Okay, this using the microstrip ring resonator, so where the samples is placed on top, so the property of the material can be determined. And okay, as mentioned earlier, the resonant mode basically controls how the signal travels. Okay, it determines how the signals travel across the structure. Okay, for example, TM010, so this is where the magnetic field is the dominant field across the structure. So, and again, it depends on the application whether the electric or the magnetic field is the dominant fields required to be determined. Okay, so the electric these two figures shows different mode. Look at how the fields, the electric fields or the magnetic field travels across two metal plates. Okay, these two represents the cavity resonators, okay, in which the samples is placed in between the two metal plates so that the property or the constant, the relative constant of the materials can be determined. Okay, this slide shows one of the example of the cavity resonators being used in order to determine the sample property. So I believe this is one of the DRA materials, the white samples in the middle. So the numbering here representing the components or the structure involved in this measurement. So the first one is the silver plates, and then second one is carbon nanotube sheet, and then the 3 and 4 is the dielectric reference and also the coaxial respectively. Okay, so each of these components have its own permittivity or the constant or the property, and each of these having its own function. Okay, why the silver plates is placed there? Will that change the property of the modes? Will that change how the signal travels, and etc.? Okay, so we are going to look at that later on. Okay, the following slides show the commercially available cavity resonators that's available from the different manufacturer, such as the Keysight, Keycom, MSI, Damascus, and etc. So depending on different types of measurement, what type of measurement needed, and different shape and also different parameters being used in order to address or to conduct different type of measurement. Okay, same goes here. There are different manufacturer of the cavity resonator, and also different mode and for different application as well.